Alright, how to construct a position time from velocity time. So that's kind of our goal, how to do this, how to go from one type of graph to another. So there's two methods to do this. I'll show you both, and you can choose whichever one works for you, whichever one you like better. So method one is we're just going to use the equations of motion. We're going to go ahead and use the equations of motion to construct our graph. Alright, so actually before this I asked you to do this, so let's just go ahead and do it on here. This is velocity time. We're going to go ahead and find the acceleration for each of these segments, right? So what's the acceleration from 0 to 3? 5, right? Plus 5. What's the acceleration from 3 to 4?
0.
4 to 5? 5 to 6? And 6 to 8? Alright, so that'll be our starting point. You should be able to easily calculate those just by finding the slope. Alright, so let's go ahead and do this. Method 1. So what we're going to do is we're going to construct kind of a little data table here. So we'll start with 0. So we'll have our time right here. So we'll go from 0 to 3 seconds. And we're going to find our displacement using the equations. Oops, displacement. Alright, so to use our equations, we should write down our givens. Well, we just found the acceleration, right? What was the acceleration from 0 to 3? 5. Okay. What's the initial velocity? That would be the velocity at 0. What's our final velocity? That would be the velocity at 3. 15. And there's one more thing we know. What else do we know? The time. What's our time? 3 seconds. 0 to 3, right? So we have 4 givens, so we should be good to go. If you have if you know 4 things, right, we can use several equations. So the one I'm going to choose is this one, the delta D VOT. Okay, so when you use this equation, what's our initial velocity? Okay, 1/2 5 times 3 squared. So that gives us a delta D of, oops, went too far. What's 45 times 1/2? 22.5. Okay, I'm going to construct one more column here. This column's going to be position. Now you have to be given an initial position. So usually the initial position would be simply 0. In which case, where am I now if I started at 0? 22.5. Alright, so we're just going to do this for each little interval. We're going to find where we are at each little interval, and then we can go ahead and plot our graph. So let's go from 3 to 4. So from 3 to 4, what's our acceleration? 0. Right here, 3 to 4, 0. What's our initial velocity, 3 to 4? 15, right? Right here we're 15. What's our final velocity? 15. And what's our time? 1 second. So be careful, even though it's been 4 seconds, we're only looking between 3 and 4. So that gives us a time of 1 second. The initial was 15. Okay, so use the same equation. We're just going to use the same one all the way through, even though you could use other things. In this case, since a is 0, what happens to that second term? Goes away, right? So this is really just delta D equals 15 times 1, which is 15. So that's my displacement. Where am I now? What's my position? Okay, so we started at 22.5, and then we went 15 more meters. Oops, this is meters. Went 15 more meters, and we're now at 37.5. All right, so why don't you guys go ahead and do that for each little segment. So we have 3 to 4, 4 to 5. So see if you can do this on your own, figure them out. I'll just kind of do it quietly up here. Okay, so hopefully you're close to getting done. Take a look at how far you've gotten so far. Check your answers. Notice what's happening. Why is our displacement negative on 5 to 6? What happened at 5? We stopped, and then what happened? Well, what's going on between 5 and 6? We're going backwards, right? Speeding up backwards. So that's why we have a negative displacement, because, well, we kind of reached our maximum. We stopped, and now we're going in reverse. So our position should be decreasing. We should have negative displacement. Same thing with 6 to 8. You should have a negative displacement, negative 20 meters, 6 to 8. All right, once you've set up, once you've found all your points, now what we're going to do is we're just going to start to plot these points. All right, so let's go ahead and set up a graph. We're going to go ahead and plot these points. So we should get to 8 seconds here. So 10, 20, 30, 40, 50. So this is my position. One, 2, 3, 4. Eight. This is my time. Alright, so you have the table. So we're graphing position, not displacement. Position, not displacement. So I told you that we started at 0. You'll usually start at 0. If not, they will tell you, okay, you started 5 meters away at the beginning, then everything would just be offset by that 5 meters. Otherwise, we'll start where it said. So at 3 seconds, where were we? 22.5. So at 3 seconds, we're 22.5. So go ahead and graph that. So 3 seconds. 3 seconds, we're 22.5. Now do not connect the dots yet. Okay, we're just going to plot them at this point. Okay, at 4 seconds, we are 37.5. 4 seconds. 37.5. Oops, I messed that up. 5 seconds, we were 45 meters away. 5 seconds, we're 45 away. Okay, 6 seconds, we're 40 away. And 8 seconds, we are 20. Okay, so that's plotting your points. Now the next thing is the final thing really, is we have to connect these points together. And we're not going to simply connect the dots. Okay, so to figure out how we're going to connect them, we are going to look at our accelerations, and we're going to look kind of at our governing equations that we used. So let's just take the 0 to 3. So notice our acceleration was 5. And here, when we look at our equation, because this was 0, you're left with delta d equals 1/2 a t squared. So what kind of function is this? A parabola, right. This is a delta d proportional to a t squared. Delta d is proportional to a t squared. Well, this is a parabolic shape. Okay, this is a parabolic shape. Now this will always happen, and actually we call this a concave up type parabola. This will always happen when acceleration is positive. Whenever you have a positive acceleration, you're going to get this delta d proportional to t squared. That's going to produce a concave up type parabola. So the way you would then connect this, and you just kind of draw this, you know, as best you can, you draw this concave up type parabola here. Concave up shape. Alright, so let's now do 3 to 4. 3 to 4, what was true about the acceleration? The acceleration was 0, which means, notice what happened to our equation. The t squared dropped out. So in other words, we could say that delta d is simply proportional to t. Right? Not t squared, but simply t, because the 0 dropped out the t squared. Well, what is this? What kind of shape? A line, right? This is a linear type graph. And this will always happen when your acceleration is equal to 0. So whenever the acceleration is equal to 0, we are going to get a linear type shape. So in this case, you will simply connect this with the line. So to do the connections, you're just going to look at what's the acceleration. Is it positive? Is it 0? Or, let's do the last one. This one, the acceleration was negative. So notice we still have the t squared function. But because it is negative, the a is negative, it's proportional to negative t squared. What kind of shape does a negative t squared give us? It's still a parabola, but what kind of parabola? Concave down type parabola. And just for, generically speaking, concave up looks like this. Concave down looks like this. So when you sketch it, you're just going to sketch a concave down parabola. Looks something like this. Okay, we have 2 more to do. Now this will always happen when acceleration is negative. Let's do the last one. What's the acceleration in 5 to 6? Negative acceleration. Therefore, what are we going to get? Concave down. This one's going to look like this. Concave down. That structure. Bless you. This is CD. And then lastly, this was an a equal to 0. What kind of graph? Linear graph. So for the very last one, we're just going to connect this by a line. So that's our final graph. That's what our final graph looks like. And this will always look better when it's on graph paper. Yours might look a little funky, but that's okay. Just do your best. Make sure it's obvious when it's concave up, concave down, or linear. Alright, so that was method number 1. That's one way you can do it, to solve it. We're using the equations of motion to find our points. So let's look at method number 2. And again, I'll show you both. You do whichever one you feel most comfortable with. Method number 2, in a nutshell, is we're going to use calculus. Specifically, we're going to use integral calculus. Well, this is not supposed to be a calculus-based class, so we're going to keep it simpler than this. And maybe some of you can remember this. When you're finding integrals, what are you really finding? You're finding the area underneath your curve. And so that's what we're going to do. So if you're going to just tune out when I say calculus, then just say find the area. Under the curve. And I'll write curve. It's almost always for this class going to be a nice line. And this is going to tell you your displacement. So finding the area under the curve will give you your displacement. So let's go back to our original graph. Where's my original graph? Alright, so let's go back to our original graph. We'll go ahead and find the areas, and then we'll just compare, and we should be getting the same answers. So let's just kind of verify. If we can do it both ways, you should get the same answer. So the first one is, we're going to find the area under this curve right here. So what shape is this? So you're finding the area of your triangle here. When we find the area, 1/2 BH, you get 1/2 of 3 times 15, which is 45. 1/2 of that is 22.5. So basically it's saying the displacement from 0 to 3 is 22.5. Well, is that what we got for our first one? From 0 to 3, we got a displacement of 22.5. Okay, so let's just do it for each segment. 3 to 4, so this would be from here to here. From 3 to 4, this is a nice rectangle, so base times height. 1 times 15. 15. That's my delta D. Okay, let's verify that's what we got before. 3 to 4, we got 15. Now you do have to figure out the positions. So that means after 4 seconds, where am I? 37.5, right? I went 22.5, then I went another 15. That's my delta D. Delta D equals 15. So essentially what we're doing by finding the areas, we're kind of bypassing this whole step right here. You can just find the delta D's a little bit faster. And then you still have to construct a position table. But let's just go through and finish it up. So 4 to 5 is a nice triangle again. 1/2 of 15 times 1 is 7.5. That's what we got last time. We're now at 45 away. Let's do 5 to 6. Now this is the only somewhat tricky part. We're going backwards, right? So what do we have to make sure happens when we find this area? We have a negative. And you can see that if you do make this negative 10 here, negative 10, 1/2 of that is negative 5. Just remember, whenever your area is in the negative axis, you're finding the area above the curve, you're going to have a negative here. So it's negative 5. Okay, and then the last one is the area of this, which is negative 20. Alright, so we essentially did the same thing. We got the same numbers. We just found it a different way. So you can use method 1, use your equations. You could use method 2, find your areas, and you should come up with the same numbers. Now the second part is the same for both. Once you have your little data table, you have to go ahead and plot it and then figure out, is it concave up, concave down, or linear. Alright, any questions on that? So anyways, just to kind of summarize, if I start with, well, I did this already, didn't I? Well, I'll just do it here. If I start with position and I want to find the velocity, what do I have to do? Find the slope. If I have a velocity and I want to find an acceleration, what do I have to do? Find the slope. Okay? Anyone know in calculus, when you're finding the slope, what you're doing? You're finding the derivative. Yeah, so this would be the derivative. If you have a weird graph where it's not so easy to find a nice slope, you would actually find the derivative. Alright, and then what if we have a velocity and we want to get to a position? What do we do? Find the area. Well, for us, we're going to find the area, but what would you do in calculus? Find the integral. Okay, now we didn't do this, but we could. What if you started with acceleration and wanted to find the velocity? What would you do? You would find the area. So if you find the area under an acceleration time graph, that'll get you to the velocity. Or if you find the integral. And when you take, most of you are probably in calculus, you will do this, okay, actually with similar functions that we're using. You'll go ahead and find derivatives and integrals and go backwards and forwards. But for our class, you're just going to be finding slopes and areas.